March 20th, 1942. A humid morning in Tokyo. Inside the Imperial Japanese Navy Technical Research Institute, Professor Hiroshi Nakamura hunched over his workbench, carefully disassembling an American bomb fuse recovered from the wreckage at Pearl Harbor. His hands, steady for over 30 years of engineering work, trembled slightly. "We will reverse engineer their technology within 3 months," he had confidently assured Admiral Yamamoto. Yet as sunlight gleamed off the intricate mechanism before him, revealing craftsmanship beyond anything he had anticipated, a cold realization formed in his mind. This simple device might represent a manufacturing advantage Japan could not overcome. Before we dive into this story, drop a quick hi in the comments and tell me where you're watching from. It really helps support the channel. This is the tale of how American industrial precision became a psychological weapon more devastating than any explosive, and how a small group of Japanese scientists came to understand the true nature of the conflict they had entered. Not merely a battle of soldiers and ships, but a confrontation between fundamentally different industrial worlds. The metal components lay arranged in perfect order across Professor Nakamura's laboratory bench. Each piece had been photographed, measured, and catalogued with characteristic Japanese attention to detail. Lieutenant Commander Shigeru Fujita, the Navy liaison to the Research Institute, watched with poorly disguised impatience. "What have you discovered, Professor?" Fujita asked, his voice carrying the crisp authority of an officer accustomed to rapid answers. Nakamura adjusted his wire-rimmed spectacles and looked up from his work. At 58, his hair had long since turned steel gray, matching the metal components scattered before him. Unlike many of his colleagues who had embraced military discipline during Japan's increasing militarization, he maintained the deliberate manner of a lifetime academic. "These fuses are remarkable," Nakamura said, selecting a small cylindrical component and holding it up to the light. "The Americans have achieved tolerances we typically reserve for precision instruments. Yet they are producing these devices by the thousands." "That is interesting from an engineering perspective," Fujita replied, "but hardly relevant to our strategic concerns. Can we duplicate them?" "Theoretically, yes," Nakamura hesitated. "Practically, I am less certain. The consistency of manufacture suggests automated production methods beyond our current capabilities." Lieutenant Commander Fujita's expression hardened. "Professor, may I remind you that the future of our nation depends upon our technical parity with the Americans. Less certain is not an acceptable conclusion." Nakamura nodded respectfully, but said nothing further. After 30 years at the Institute, he had learned when to voice concerns and when to remain silent. This was a moment for silence. 500 kilometers away in Osaka, another scientist was reaching similar conclusions. Dr. Masatoshi Okada, former head of metallurgy at Osaka Imperial University and now director of the Army's Material Testing Laboratory, examined the aluminum housing of an American proximity fuse. His assistant, Captain Toshiro Tanaka, watched as the older man conducted a series of hardness tests. "The aluminum alloy is nothing special," Okada said, making a notation in his research journal. "It is the consistency that is remarkable. I have tested samples from 6 different fuses. The variation in hardness is less than 1% between all specimens. Our manufacturers can surely match this," Captain Tanaka suggested. Okada set down his instruments and looked directly at the young officer. "Captain, do you know how many factories in Japan can currently achieve such consistency?" 2, perhaps 3. And they produce specialized optical equipment in small quantities, not military hardware in the thousands. "What are you suggesting, Doctor?" "I am not suggesting anything. I am stating facts. American industry is operating at a level of precision we have not achieved." Okada returned to his measurements, his weathered hands moving methodically. "These components were not individually crafted by master technicians. They were mass-produced, yet maintained tolerances we struggle to achieve even in our finest work." The captain stiffened, his pride wounded. "The spirit of our workers will overcome any technical advantage. The Americans are soft industrialists who have never known hardship." Okada merely nodded, having learned long ago that patriotic certainty was best left unchallenged, even when contradicted by empirical evidence. He had survived the political purges of academic institutions in the 1930s, by developing such discretion. In Tokyo, Professor Nakamura continued his examination late into the night after Lieutenant Commander Fujita had departed. His young assistant, Kenji Yamada, remained by his side, taking detailed notes. Unlike many of the military personnel attached to the institute, Yamada had been Nakamura's student before the war and shared his mentor's curiosity about fundamental scientific questions. "Professor," Yamada said quietly, "I have been studying the timing mechanism. The gear teeth are cut with remarkable precision." Nakamura nodded. "I noticed the same. Have you measured the variation between teeth?" "Yes, less than 0.02 millimeters across all specimens." "And how many specimens have we examined?" 23 complete fuses and partial components from 15 others. Nakamura removed his glasses and rubbed the bridge of his nose. "And the variation holds across all of them? Even those recovered from different locations?" "Yes, Professor. The fuses recovered from the Philippines show identical tolerances to those from Pearl Harbor. They appear to have been manufactured to identical specifications. That suggests standardized production methods across multiple American factories," Nakamura said, almost to himself. "Their industrial base is not merely large, but integrated in a way ours is not." The implications hung silently between them. Japan's manufacturing base consisted of numerous small to medium workshops, each with their own slightly different methods and standards. The Zaibatsu, Japan's large industrial conglomerates like Mitsubishi and Sumitomo, had modern factories, but even they lacked the standardization evident in these American components. In June of that year, an opportunity to directly compare Japanese and American manufacturing arose under tragic circumstances. Following the American attack on Midway, which resulted in the loss of 4 Japanese aircraft carriers, salvage teams recovered American ordnance that had failed to detonate. Among these were several 500-pound aerial bombs with intact fuses. Commander Hideki Takahashi of Naval Intelligence personally delivered 3 of these fuses to Professor Nakamura's laboratory. His presence underscored the increasing importance military leadership placed on understanding American technical capabilities. "These were recovered at great cost," Takahashi said, placing a waterproof container on Nakamura's workbench. "Several salvage divers were lost recovering these items." Nakamura bowed slightly. "Their sacrifice will not be wasted. We will learn everything these devices can tell us." Over the following 3 days, Nakamura and his team disassembled the fuses with painstaking care. Each component was compared against both American fuses previously examined and comparable Japanese designs. The results prompted an unprecedented meeting between Army and Navy technical teams, a rare cooperation between services that traditionally guarded their research jealously. The meeting convened in a secure conference room at Imperial General Headquarters in Tokyo. Professor Nakamura and Dr. Okada sat at a table crowded with military officers, bureaucrats from the Ministry of Munitions, and representatives from major industrial firms. Vice Admiral Matome Ugaki, Chief of Staff to the Combined Fleet, presided. "Gentlemen," Admiral Ugaki began, "we have brought you together because reports from our technical research institutes suggest a concerning disparity between American and Japanese manufacturing capabilities. Professor Nakamura, please present your findings." Nakamura stood, acutely aware that his next words would challenge many deeply held beliefs about Japanese technical prowess. He began with diplomatic caution. "Most honored colleagues, over the past 4 months my team has conducted detailed analysis of American bomb fuses recovered from various theaters of operation. We have compared these with our own designs, focusing specifically on manufacturing precision rather than functional design." He placed a projector slide showing microscopic photographs of gear teeth from both American and Japanese fuses. "As you can see, the American components show machining consistency that exceeds our current production standards by a significant margin. More importantly, this precision is maintained across thousands of units, suggesting automated manufacturing techniques we have yet to fully implement." A murmur ran through the room. Major General Takeo Yasuda of the Army Technical Bureau rose to his feet. "Professor, Are you suggesting Japanese craftsmanship is inferior to American mass production? Our workers take personal pride in their work. Each component is checked by human eyes and hands, not soulless machines. Nakamura chose his response carefully. The dedication of our workers is beyond question, General. However, the precision I am describing is not achievable by human hands alone, regardless of skill or dedication. Modern aerial warfare requires consistency that only machine tooling and standardized processes can provide. Dr. Okada added his voice to the discussion. If I may, the metallurgical analysis reveals another concerning factor. The aluminum alloys used in these American components are uniform in their composition. Our testing reveals variation of less than 0.5% in key elements. Our own production shows variations of up to 5% between batches from different suppliers. This technical discussion continued for over 3 hours. As military officers and industrialists debated the implications, a fundamental truth became increasingly clear. Japan had entered a conflict with an industrial power whose manufacturing capabilities far exceeded their own. Takanobu Maeda, director of production at Mitsubishi Heavy Industries, finally addressed the uncomfortable reality. Gentlemen, what these scientists are describing is not merely a matter of better machines. The Americans have created an entirely different approach to manufacturing, what they call statistical quality control. We have some knowledge of these methods, but have not implemented them widely. Admiral Ugaki's expression remained impassive, though his voice carried new tension. What would be required to adopt these methods across our defense industries? Maeda hesitated. A complete reorganization of our manufacturing philosophy. New precision machinery, most of which we would need to design and build ourselves due to embargoes. Training programs for thousands of workers. And most challenging, time perhaps 2 to 3 years to fully implement. The room fell silent. Everyone present understood that Japan did not have 2 to 3 years. The war in the Pacific was already straining resources beyond sustainable levels. Vice Admiral Ugaki finally broke the silence. Professor Nakamura, Dr. Okada, you will form a special research group to further study these American components and provide specific recommendations for our most critical munitions. Director Maeda, your company will implement whatever changes these scientists recommend, with full government support. As the meeting concluded, Nakamura and Okada found themselves walking together through the headquarters corridor. Despite having corresponded professionally for years, this was their first meeting in person. They do not truly understand what we are telling them, Okada said quietly. No, Nakamura agreed. They hear our words but cannot accept their meaning. To acknowledge the full implications would require questioning decisions already made at the highest levels. Yet we must continue our work. Of course, what else can we do? The special research group formed by Admiral Ugaki's decree began work immediately, combining the resources of both Army and Navy technical bureaus. Nakamura and Okada established laboratories in Yokosuka, safely distant from Tokyo, and the increasing American air raids. By September 1942, they had examined over 100 different American components, from bomb fuses to aircraft parts recovered from crashed planes. The picture that emerged was consistent and troubling. American industry was producing precision components at a scale and quality that Japanese manufacturing could not match. The implications extended far beyond bomb fuses, aircraft engine tolerances, ammunition consistency, radio equipment reliability, all showed the same pattern. One afternoon, as Nakamura and Okada reviewed reports from a subcontracted manufacturing plant, a naval messenger arrived with an unusual delivery, fragments of an American B-17 bomber downed near Rabaul. Among the twisted aluminum were several remarkably intact instruments. These were specifically requested by Imperial headquarters, the messenger explained. The commanding general wishes to know if American aircraft instruments demonstrate the same precision as their weapons components. Okada examined the shattered remains of an altimeter. Despite the damage, the craftsmanship was evident. Please inform the general that we will provide a complete analysis within 72 hours. After the messenger departed, Nakamura carefully extracted a relatively intact airspeed indicator from the wreckage. Look at this calibration mechanism, Masatoshi. The precision is remarkable. And yet these instruments are being produced by the tens of thousands, Okada replied. My contacts in the Navy tell me that American factories have already replaced all the aircraft lost at Pearl Harbor. That evening, alone in his temporary quarters, Professor Nakamura wrote in his personal journal something he had done every night since his university days. His entries had grown increasingly pessimistic as the war progressed. Today I held in my hands proof of what I have feared since examining the first American fuses, he wrote. We have entered a conflict with a nation that has transformed precision from an expensive luxury to an industrial commonplace. Our leadership believes spirit can overcome material superiority, but spirit cannot manufacture bearing assemblies with tolerances measured in microns. I fear we have awakened a sleeping industrial giant and filled him with a terrible resolve. The next morning, Nakamura was surprised by an unexpected visitor. Lieutenant Commander Fujita arrived with Kenji Yamada, Nakamura's former assistant who had remained in Tokyo. Professor, we have brought something you must see immediately, Fujita said, dispensing with formal greetings. Yamada carried a wooden crate, which he placed carefully on the laboratory workbench. What is this, Lieutenant Commander? Nakamura asked. Components from an American aircraft carrier radar system, recovered by Submarine Special Operations Group from the Solomon Islands. Nakamura's eyes widened. Radar technology represented one of the most significant technological gaps between Japanese and American forces. Japan had developed functional radar systems, but they were bulky, limited in range, and produced in small numbers. American radar, particularly the newer microwave systems, far surpassed Japanese capabilities. How did we obtain these? Nakamura asked, already opening the crate. A commando operation, Fujita replied tersely. No further details are necessary. Inside the crate lay several components, including waveguides, a magnetron assembly, and various electronic modules. Nakamura and Okada spent the next 6 hours examining them in meticulous detail. The machining of these waveguides is extraordinary, Okada said. The tolerances are maintained along curved surfaces, something extremely difficult to achieve consistently. Nakamura nodded, absorbed in examining a circuit assembly. And look at these electrical components. The resistors are color-coded and standardized. I would wager every American radar set uses identical parts that can be interchanged as needed. Our radar components are essentially handcrafted, Okada replied. Each set requires individual calibration by a trained technician. The radar components reinforced what they already knew, but at a more sophisticated technological level. American industry wasn't merely producing simple mechanical devices with high precision. They were manufacturing complex electronic systems to the same exacting standards. That evening, a secure telephone call from Tokyo added a new dimension to their research. Japan's naval attaché in Switzerland had forwarded a translated article from an American business magazine describing new quality control methods implemented across United States defense industries. Listen to this, Nakamura said to Okada, reading from the report. The implementation of statistical process control has reduced defect rates by 80% while increasing production speeds by 30% across participating factories. Workers no longer inspect each component individually, but monitor statistical variations in automated processes. They've created manufacturing systems that maintain precision without relying on master craftsmen, Okada observed, a fundamental philosophical difference. By November 1942, the Special Research Group had compiled their findings into a comprehensive report for Imperial General Headquarters. The document detailed specific technical disparities between American and Japanese manufacturing, with recommendations for addressing the most critical gaps. The response was not what they had anticipated. Instead of the wide-ranging industrial reforms they had advocated, military leadership authorized only limited modifications to certain critical munitions factories. Resources were simply too scarce, and the immediate demands of the war effort took priority over long-term manufacturing transformation. Professor Nakamura found himself reassigned to a more narrowly focused project, improving the reliability of fuses for Japanese naval shells. Dr. Okada returned to Osaka to oversee quality improvements at aircraft engine plants. Their broader warnings about American industrial capacity went largely unheeded. Despite these setbacks, both scientists continued their work with diligence. By early 1943, Nakamura had developed modified production methods that improved Japanese fuse reliability by nearly 30%, though still falling short of American standards. Okada's work resulted in more consistent aircraft engine performance, extending the average operational life of fighter engines by significant margins. In April 1943, a year after beginning their study of American components, Nakamura and Okada met again in Tokyo. The occasion was a technical conference on resource conservation in munitions production, finding ways to maintain effectiveness while using less of Japan's increasingly scarce raw materials. After the formal sessions concluded, they found a quiet corner in a small restaurant near the Imperial Palace. It was one of the few establishments still offering something resembling pre-war cuisine, though the portions had grown noticeably smaller. "How is your work progressing, Hiroshi?" Okada asked, pouring tea for his colleague. "We make incremental improvements," Nakamura replied. "Our naval shell fuses now detonate with 86% reliability, better than the 70% we started with, but still far from the 95% estimated for American ordnance. Similar results in Osaka. We improve, but the gap remains." Okada lowered his voice. "Have you seen the production figures from America? They're Essex-class aircraft carriers. They've launched 8 in the past year. We've completed 1 fleet carrier in the same period." Nakamura nodded grimly. "I've heard rumors that a single American shipyard, something called Kaiser in Portland, is producing Liberty ships in less than 2 weeks per vessel. Our most efficient yards require 6 months for comparable ships." Their conversation was interrupted by air raid sirens, an increasingly common occurrence in Tokyo. This raid proved to be a false alarm, but it underscored the changing realities of the war. American bombers were now regularly appearing over the Japanese home islands. As they prepared to return to their respective posts, Okada handed Nakamura a small package wrapped in brown paper. A sample from a crashed B-29 bomber, the most advanced aircraft in the world. Study it when you have opportunity. The package contained fragments of a B-29 supercharger, a critical component that allowed the bomber's engines to operate efficiently at high altitude. Nakamura spent a week analyzing it, confirming what he already knew. The precision manufacturing gap between America and Japan was not closing. If anything, it was widening as the war progressed. By mid-1944, the strategic situation had deteriorated dramatically for Japan. American forces advanced steadily across the Pacific, supported by an industrial output that seemed limitless. The Special Research Group's laboratories in Yokosuka were relocated inland as American carrier aircraft began regular strikes against coastal facilities. Professor Nakamura now split his time between improving existing weapons and a new, more desperate assignment, developing improvised munitions that could be manufactured with minimal industrial requirements. His team designed simplified fuses that could be produced in small workshops, trading precision and reliability for ease of manufacture. In Osaka, Dr. Okada faced similar challenges. His laboratory, once focused on improving quality control, now worked primarily on material substitution, finding ways to build aircraft engines with increasingly scarce chromium, nickel, and aluminum alloys. The technological disparity that Nakamura and Okada had identified in those first American bomb fuses had expanded into every aspect of the war effort. American planes, ships, tanks, and munitions continued to improve in both quality and quantity, while Japanese production struggled simply to maintain basic capabilities with dwindling resources. In February 1945, Professor Nakamura received unexpected orders to report to an underground facility near Mount Fuji. Upon arriving, he discovered a large-scale effort to reverse engineer captured American equipment, from radios to aircraft components. Dr. Okada was already there, leading a team analyzing materials from a crashed P-51 Mustang fighter. The facility director, Major General Seizo Arisue of Military Intelligence, explained their new assignment. "We are creating a comprehensive technical archive of American military technology. This information must be preserved, regardless of how the current conflict resolves itself. The unspoken implication was clear. Japan's military leadership was preparing for defeat. This archive would preserve technical knowledge for a future Japan that would need to rebuild. For the next 3 months, Nakamura and Okada worked with dozens of scientists and engineers, meticulously documenting American technical achievements. The work was periodically interrupted by air raids, with each scientist responsible for evacuating specific documentation in case of direct attack. During this period, Professor Nakamura began writing what would later be considered his most important work, a comprehensive analysis titled Precision as Strategic Advantage: American Manufacturing Methods and Their Military Applications. The document was not merely technical, but included philosophical observations about the different approaches to industrial production between the two nations. The American approach treats precision as a systematic property rather than an individual achievement, he wrote. Where Japanese craftsmanship seeks perfection through the skill of the individual artisan, American industry creates systems where precision emerges from the process itself, maintained by statistical control rather than personal attention. Neither approach is inherently superior in all applications, but in modern warfare, the American system demonstrates overwhelming advantages in scale and consistency. As American forces approached Japan itself, the underground facilities work took on greater urgency. In June 1945, with American bombers now operating virtually unopposed over Japan, Nakamura and Okada were ordered to relocate once more, this time to a remote mountain facility in Nagano Prefecture. Before leaving Tokyo, Professor Nakamura visited his old laboratory at the Imperial Japanese Navy Technical Research Institute one final time. The building had been damaged in air raids, with several wings reduced to rubble. In his former office, he found Lieutenant Commander Fujita, now promoted to commander, sorting through technical documents. "Professor," Fujita acknowledged with a tired nod, "I'm selecting critical research to be preserved. Most records will be destroyed before the Americans arrive." "Then our defeat is considered inevitable?" Nakamura asked directly. Fujita paused, then answered with surprising candor. "The war was lost the moment we failed to understand what you showed us in those first American bomb fuses. We saw only mechanical devices. You saw the true face of our enemy, an industrial giant that had transformed precision manufacturing from an art to a science." Nakamura was struck by this admission from a man who had once dismissed his concerns as defeatist. "And now we preserve what knowledge we can for future generations. Japan will need to rebuild. Perhaps they will listen then to what you tried to tell us 3 years ago." In the final weeks of the war, as American forces prepared for an invasion of the Japanese home islands, Professor Nakamura and Dr. Okada completed their comprehensive technical archive. Hidden in a series of mountain caves, waterproofed and sealed in ceramic containers, the documents preserved not only technical specifications, but the more fundamental lessons about industrial organization and quality control that Japan would need to adopt. On August 15, 1945, Emperor Hirohito announced Japan's surrender. For Nakamura and Okada, the news brought not surprise but a somber relief. The work they had been doing to preserve technical knowledge would now serve a different purpose, helping to rebuild their shattered nation. In the autumn of 1945, as American occupation forces established control over Japan, both scientists were interviewed by the Scientific Intelligence Team of the United States Strategic Bombing Survey. The Americans were assessing Japanese technical capabilities and were particularly interested in understanding why Japan had failed to match American precision manufacturing, despite having captured and studied numerous examples of American technology. Colonel Robert Wilson, an industrial engineer before the war, led the interview with Professor Nakamura in a requisitioned office at Tokyo University. "Professor, our analysts were surprised by the detailed technical knowledge your teams possessed about our equipment," Wilson began. "You clearly understood the manufacturing advantages we held, yet Japan never managed to close the gap. Why?" Nakamura considered the question carefully. Understanding the technical requirements for precision manufacture is not the same as possessing the industrial infrastructure to implement that understanding. Japan lacked the machine tool industry, the quality control systems, and the industrial standardization necessary to match American production methods. More fundamentally, we lacked the philosophical approach to manufacturing that your country developed, the systematic view of precision as a property of systems rather than individuals. You're referring to the statistical process control methods developed by Bell Laboratories and others. Yes. We were aware of these approaches before the war, but considered them inconsistent with Japanese manufacturing traditions, which emphasized the skill of individual craftsmen. By the time we recognized their critical importance, it was too late to transform our industrial base while fighting a global conflict. Colonel Wilson nodded thoughtfully. Your analysis matches our own conclusions. It's remarkable that you identified this so early in the conflict. Not early enough to make a difference, Nakamura replied quietly. In the years following the war, both Nakamura and Okada played significant roles in Japan's industrial reconstruction. Professor Nakamura joined the newly formed Japan Standards Association, helping to establish nationwide industrial standards based partially on American models. Dr. Okada returned to academia, teaching a new generation of engineers at Tokyo University with a curriculum that emphasized statistical quality control and precision manufacturing methods. The lessons they had learned from those American bomb fuses became foundational principles in Japan's post-war industrial philosophy. The very precision that Japan could not match during the war became a hallmark of Japanese manufacturing in the decades that followed. By 1960, less than 15 years after the war's end, Japan had transformed its industrial base. Companies like Toyota adopted and then improved upon American quality control methods, eventually surpassing their American counterparts in manufacturing precision and consistency. In 1968, an elderly Professor Nakamura was invited to give a guest lecture at the Massachusetts Institute of Technology on the evolution of Japanese manufacturing methods. During the question and answer session, a young engineering student asked him to identify the most important factor in Japan's industrial renaissance. Understanding that precision is not merely a technical achievement, but a philosophical approach to production, Nakamura replied. This understanding came at great cost during the war, when we discovered that all our skill and dedication could not match the systematic precision of American industry. The lesson was painful, but we learned it well. Today, Made in Japan is becoming synonymous with the very precision we once could not achieve. The story of Professor Nakamura and Dr. Okada remained largely unknown outside technical circles until the 1980s, when historians began examining the technological aspects of the Pacific War in greater detail. Documents preserved in their technical archive, including Nakamura's analysis of American manufacturing advantages, provided valuable insights into how technological disparity influenced the war's outcome. Perhaps the most poignant artifact from this period was Professor Nakamura's final journal entry before Tokyo's surrender, discovered among his papers after his death in 1972. Tomorrow, our nation surrenders to a power whose true strength we recognized too late, he wrote. The precision gears in those first American bomb fuses foretold our defeat more clearly than any intelligence report or battlefield loss. They revealed not merely superior technology, but a different way of thinking about production, a systematic approach that transformed precision from an expensive luxury into an industrial commodity. If Japan is to rise again from these ashes, we must learn this lesson well. The future belongs not to the nation with the greatest individual skill, but to the one that can make precision routine. In the decades following World War II, Japan did indeed learn this lesson, transforming its industrial base into one of the world's most sophisticated manufacturing powers. The precision that Japanese scientists like Nakamura and Okada had once observed with concern in American bomb fuses became the very standard that Made in Japan would come to represent worldwide. The story of their discovery remains a powerful reminder of how fundamental technological advantages can determine the course of history more decisively than any single battle or campaign. It also demonstrates how the painful lessons of defeat can, when properly understood, become the foundation for future success. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.